let's talk about some conversions that alcohols can actually do. Really, up until now, we were forming alcohols. Let's take an alcohol and convert it into something else. Like we say here, we can convert alcohols into nearly any other functional group. So let's start by making alcohols into alkyl halides. If I have a tertiary alcohol, right, so 3R groups on the alcohol, if I use a strong acid, right, HCl, HBr, first thing that happens is we'll protonate the alcohols, right? Because remember we said alcohols are weak bases, right? We put that in the presence of a strong acid. We will protonate it. So here we have our protonated alcohol, or our oxonium ion. If it is tertiary, and only if it is tertiary, the leaving group will simply leave on its own, giving us a stabilized tertiary carbocation. Okay? Remember, carbocations are more stable the more R groups can donate electron density into them. So I form a carbocation, which can be attacked by the halide ion, so chloride or bromide. Okay? That'll give us an alkyl chloride or bromide, but that only works for tertiary because a secondary or primary carbocation is not stable enough. Okay? This is an SN1 reaction because right here, the slow step is formation of the carbocation, and there's only this one molecule right here involved in the rate limiting step. So unimolecular, right? That's what that one is. Just one molecule. It's first order when we're forming that carbocation. If I have any other alcohol, I need a reagent that converts the OH into a better leaving group. So OH minus itself is too unstable to be a good leaving group. So hydroxide, always remember that hydroxide is not going to be a good leaving group. Typically, it's too strong of a base. It'll just come right back in and kick back out whatever it was that added. If I have a good leaving group, a halide can displace it by an SN2 mechanism. So that's where SOCl2, thionyl chloride, CLS, Cl with the double bond O on S. Okay, so sort of looks like acetone, but with S in the middle and then two chlorides coming off of it. What happens is, I'll just give you the first step here. The O of the alcohol attacks the S of thionyl chloride, brings the electrons up onto the oxygen. What's next is they'll come back down and kick off a chloride. So we've added this S double bond O Cl group, okay, which now makes a good leaving group. So the chloride that got kicked off of thionyl chloride comes in, attacks the carbon, kicks off the leaving group. So the Cl bond is broken. We end up with an alkyl chloride by an SN2 mechanism, where that chloride attacked from the exact opposite direction that the leaving group was leaving, and it happened simultaneously. So PBr3, very similar, right? Phosphorus tribromide. This mechanism is actually very simple. The O will attack the phosphorus and kick off one bromide. So I have OPBr2. That bromide comes in, attacks the carbon, and kicks off the leaving group. POBr2 is a much better leaving group than hydroxide because those two bromines can remove some of that O-'s electron density. Okay? Both of these are SN2, okay, which means we'll have inversion of stereochemical configuration. So very important consequence there. If I have a optically active alcohol like this R2-butanol, if I react that with either of these reagents, let's just do thionyl chloride, we'll have inversion of configuration. The resulting alkyl chloride will be S. Right? Because the chlorine, right, will form the leaving group on the oxygen. The chloride will attack it from the opposite side. Okay? So very important to understand that stereochemical consequence that either of these, if I have a chirality center on the alcohol, it will be inverted when we do either of these. The SN1 reaction does not do inversion, it does racemization. Okay? Because this carbocation is flat, the nucleophile can add equally well from either side, so we'll end up with a mixture of the two stereoisomers if that's an option.